Hello guys, welcome back. Last time we finished elimination reaction. This time we'll be doing reaction with metals and aryl halides, right? Now let's get started. First reaction will be reaction with sodium metal, right? This is very important reaction, Wurtz reaction, right? Rx plus 2 moles of Rx plus 2 moles of Na will give Rr and NaX. Now take note that this Rx should be a both the alkanes should be same, right? You can't do methyl bromide and ethyl bromide because you'll get a mixture of products. If you see, right, methyl can react methyl bromide will give ethane, ethyl bromide will give propane, ethyl bromide will give butane, right? So you'll get a mixture of products. So that's why it's used to produce only symmetrical alkanes using symmetrical alkanes, right? So if you use 2 moles of ethyl bromide, you get butane, right? It's a symmetrical alkane. Next is reaction with zinc, Franklin reaction. It's just same as Wurtz reaction, but zinc has a valency of 2, right? So only 1 mole of zinc is required for the reaction. Next, reaction with magnesium. This is a important reaction, formation of a Grignard reagent. If you take an alkyl halide and react it with magnesium in presence of dry ether, you will form alkyl magnesium halide. Okay, this dry ether will solvate alkyl magnesium halide and drive the reaction forward. That's why dry ether is used. Alright. So this alkyl magnesium halide later will be used for many things in formation of alcohols and all that. So it is a very important compound, right? So again, there's a bond polarity. This is ionic and this is covalent. Okay, but no bond can be pure fully ionic or fully covalent. But for the most of it, it's ionic and covalent. This follows a free radical mechanism. So that's why it forms a planar species and can form a racemic mixture. Right? I've told you about planar species. It can attack from top and bottom and form a racemic mixture. Right? These are some examples. Okay, if you have a phenyl ring connected to a alkyl halide, right? So when this bromine goes and this free radical will resonate with this ring, right? So the mgbr can either be put at ortho position or para position. That is also one possibility, right? Okay guys, next we go to aryl halides, right? Formation of aryl halides from benzene. Now this, like, many people have a confusion. They do Cl2 and energy and they write chlorobenzene. Guys, you cannot do that because this is an electrophilic substitution reaction. For the formation of electrophile, that sunlight Cl2 Hmu is not enough, right? So now with reaction with FeCl3 and AlCl3 are just Lewis acids which help in the formation of the electrophile, right? So yeah, the reaction is very important and you have to note it down, right? This is again iodination. Okay, now you have this thing, toluene, right? If you react toluene with this, again I told you when the electrophile is formed, it resonates, right? The electrons, it forms a resonating structure when the electrophile is formed. So when electron density, chlorine can either attack at ortho position or para position where it's electron deficient, right? The plus charge will resonate. That plus charge shows electron deficiency, and chlorine has excess of electrons, so it can attack here or here, right? Next is from aniline. From aniline, if you use diazotization mixture, which is NaNO2HCl, between 0 to 5 degrees, temperature is also very important. You get benzene diazonium chloride, right? Now this is again reaction mechanism, not that important for Cbse, but you can take a note of it, right? uh, okay. Now Sandmeyer's reaction, diazonium salt with CuCl2HCl, CuBr2HBr give chlorobenzene, bromobenzene, that is Sandmeyer's. Potassium iodide heat, iodobenzene. Okay, now if you just use CuHCl, CuHBr, you get the same products but comes under another name, Catterman-Koch reaction. Okay, now you have fluorination also. If you take a diazonium salt and use HbF4 and heat, you get fluorobenzene, right? This is an important reaction. It comes in few conversions. Okay. Next, okay, chemical properties. Okay, now first property we'll be talking about is nucleophilic substitution reaction. All right, so nucleophilic substitution reaction, let's see why it does not go nucleophilic substitution reaction, right? So first of all, let's see this resonating structure. Okay, when this electron goes here, it forms a double bond here, right? This that's the first criteria. Double bonds are harder to break than single bonds. So in resonance, it actually forms some sort of double bond character. That's why it's not easily broken. Okay. Next thing, if we look at this place, it has like 6 electrons around it, right? And one bonded uh, lone pair I'm talking about, like 3 lone pairs, right? So you can see the electron cloud is repelling the incoming nucleophile, right? The nucleophile is coming and the electron cloud is repelling it. That's one more thing. Third thing is this carbon, right, is sp2 hybridized. When sp2 hybridized, so it has like around 33.3% s character, right? So when s character ka percent increases, electronegativity also increases. So now electronegativity has increased, right? So now like the polarity of the bond has decreased. Now let's see, try to understand, guys. Like electronegativity, how, what depends, like polarity of a bond, like one is less electronegative, other one is more electronegative, right? Then the bond is very polar, right? But for example in HCl, right? H is like hydrogen chloride, right? So chlorine is very electronegative, while as fluorine is not that much. That's why the bond is very polar. But if you take if the electronegativity of, if you take an atom AB and B is more electronegative than A, and electronegativity of A increases, the bond polarity decreases, right? You guys are understanding, right? Now if the bond polarity decreases, it's tougher to break the bond, right? Yeah, less polar bonds, it's tougher to break it, right? So that's one more reason. And wait, the next reason is here. Yeah, this is the bond polarity thing. Okay. Next, when this X leaves the phenyl carbocation, one more thing, chlorine leaves, right? Chlorine leaves taking one electron pair, right? And this is a phenyl carbocation form, right? That is highly unstable, right? That's why it does not undergo reaction. These are the three reasons you have to write in exam. Okay. Okay, this is Dove's process. We don't use it that much in conversions, but sometimes you can. All these are important. Aqueous sodium hydroxide, 623 Kelvin, 300 atm, right? This forms sodium phenate. On hydrolysis will give phenol, right? Is used in an industrial manufacture of phenol, right? Then again, this is fitting reaction. Use sodium dry ether, and there's one more, words fitting reaction. Okay. Then reaction with copper, lithium. These two are not important, but reaction with magnesium is important to form magnesium Grignard reagent, right? Next is electrophilic substitution. Okay, this is a, yes. X, okay, it increases the electron density in orthopara direction. But yeah, also you know that chlorine is a minus I group, right? It's not a plus I group. It like withdraws electrons, it wants electrons, right? It's a minus I group. It has a minus I effect, or and also a plus M effect. Plus M matlab resonance, like it gives the electron in resonance, right? That's plus M effect. A special case for halogen, minus I dominates plus M. Okay, so it is actually a deactivating orthopora directing. For example, if you take some group like aniline, okay, and aniline, and you react with bromine, you get three pro, like all the three, ortho, para ortho. There are two ortho positions, like at 2, 4 and 5, right? 2, 4 and 5. So if you take aniline, right, this is 2, this is 4, this is 6, right? This is 6. Bromine will be attached everywhere because it is like highly activating, right? It does not have that minus I effect, but chlorine has minus I effect. That's why it's deactivating and orthopara directing, right? That is very important, that X is a deactivating and orthopara directing group. Yeah, for example, if you see chlorine Cl2 AlCl3, right? This is again electrophilic substitution, right? This is a minor product due to electron repulsion between two chlorine, and this is the major product, right? This is nitration. Concentrated HNO3, concentrated H2SO4, very important. You get major minor again. This is sulfonation. concentrated H2SO4, you get SO3H. Okay, don't write SO2 here. Benzene sulfonic. Yeah, this is a like it has more preference. No, so 2-chlorobenzene sulfonic acid. Okay, next reactions are also very important. It's a type of an electrophilic reaction, substitution reaction. Chlorine CHCl CH3Cl anhydrous AlCl3. Okay, CH3 प्लस होगा और यहाँ अटैच हो जाएगा. इलेक्ट्रोफिलिक सब्स्टिट्यूशन, फ्रिडल-क्राफ्ट alkylation, and here now you have uh, propane chloride, right? Now it forms an electrophile and it jumps here, rearrangement happens, then this forms this compound, right? This is also important. You should always like give the most stable compound in Friedel-Crafts acylation. Now Friedel-Crafts alkylation, right? This is acyl chloride is used, and breaks this bond breaks and it is attached here as in like this becomes the electrophile and it's attached here. Okay, it's called orthochloroacetophenone, right? That's it, guys. That's it for this chapter. Please let me know how I can improve on teaching, if I'm going too fast or too slow or I'm missing out concepts or anything. That's it. Study hard. Okay. Revise other notes also. If you have time, I'd really suggest you to do this chapter from physics wala. But like if you don't have time and you have an exam tomorrow, or like if you have already studied and you just want you just want the notes with some basic explanation, you can always come here. Thank you guys. Have a nice day.